Now let's proceed to our last speaker, and she's going to talk about the carbon management networks. So let us hear from Dr. Beatriz Belmonte of UST.
Good
Ma'am
morning,
Beatriz?
everyone. Yes, can you hear me? Oh,
Yes, we can hear you.
let me just share my screen.
Yes, ma'am, go ahead. Okay, thank
Okay,
you.
I'm currently sharing my screen. Can you see my screen? Can I have a confirmation if my screen is
Yes,
okay?
yes.
Okay, thank you. Okay, so you already see my screen. You can already see hear my voice.
Yes, ma'am, loud and clear.
Okay, thank you very much. Good morning, everyone. My presentation for today will focus on the use of process systems engineering approach in developing a systematic framework for large-scale biochar-based carbon sequestration. And this work is co-authored with Dr. Francis Benjamin, a colleague of mine, and Professor Raymond Tan from De La Salle University. So here is the outline of my presentation. To begin with, atmospheric carbon dioxide concentration recently reached 415 parts per million. And this situation would require the massive deployment of technologies to remove carbon dioxide from the air and bury it below the ground. And so researchers suggest that it is now necessary to approach near zero future carbon emissions in order to stabilize climate. And they have suggested that there may be a need to deploy negative emission technologies. So, what are negative emission technologies? Negative emission technologies are means of achieving net removal of greenhouse gases from the environment such that atmospheric concentrations are reduced below the level that would have resulted without their deployment. In our current climate situation, a permanent or long-term storage of carbon is indeed critical and more beneficial. And biochar is a scalable negative emission technology that has received substantial attention in the scientific community, mainly due to its significant potentials to combat climate change, while at the same time improving soil properties. So, how can biochar help mitigate climate change? Of course, we all know that carbon can be stored in soil as crop residues or humus, but crop residues usually oxidize into carbon dioxide and are released into the atmosphere within a couple of years. And we also know that the lifetime of carbon in humus is typically less than 25 years. But when the biomass is instead pyrolyzed, a stable solid product is produced that largely consists of a recalcitrant carbon fraction with a half-life of a few centuries in soil. Now, the carbon-rich product is called biochar when it is stored below the ground for long-term removal of atmospheric carbon. Direct sequestration in biochar coupled with beneficial secondary effects, as you can see in the slides, can potentially mitigate 130 gigatons carbon over the course of the century. But biochar is a negative emission technology that has been rated as being intermediate in terms of technology readiness level. So what does this imply? This implies that system-level integration still needs further research for the optimal deployment of biochar as a carbon sequestration technology. And in fact, the current literature on biochar is highly fragmented, with a significant research gap in system-level analysis to synchronize production, logistics, and application into a sustainable carbon management strategy. And process systems engineering and the allied subdiscipline of process integration can provide a framework to allow the potential benefits of biochar systems to be optimized. Process systems engineering focuses on the use and development of computer-aided tools to guide decision-making for a particular type of problem. And my work focuses on developing computer models to provide decision support for the use of carbonized biomass as a soil enhancer and as a form of carbon sequestration. Computer-aided planning of biochar-based carbon management networks will be needed or necessary to maximize greenhouse gas reductions while minimizing any potential adverse environmental impacts. And these models can help decision makers to understand and optimize the cost benefit aspect of these systems or biochar systems to accelerate their commercial deployment. The promising results of biochar application to soil can be potentially optimized through biochar-based carbon management networks with the aid of process systems engineering and in particular mathematical programming. And in this work, the term biochar-based carbon management networks is proposed to describe systems that are intended to strategically plan carbon sequestration via systematic production and allocation of biochars for long-term storage to agricultural lands to simultaneously improve soil properties. And this study develops an optimization framework for biochar-based carbon management networks by accounting for relevant and practical aspects of biochar research, as you can see in this slide. And this work is the first to integrate this aspect of biochar research into a systematic framework for the high-level planning of large-scale biochar-based carbon management networks. And such framework provides innovative biochar systems concepts to fill the research gap in the global biochar literature. So the framework can be developed with the aid of mathematical programming, and these are the inputs and outputs of the model. So basically, we are given a set of n biochar sources, which are production plants or pyrolysis plants, and a set of m biochar sinks, which are agricultural lands or any tract of land. The problem is to determine the optimal allocation of biochar to maximize carbon sequestration and profitability. So this is the mathematical model formulation. The problem is concerned with mathematical optimization involving two objective functions to be optimized simultaneously. And one of the objective functions is to maximize the carbon sequestration of the system throughout the period specified by the model. The second objective function is to maximize annual profitability during the planning horizon. These equations show that the total amount of biochar produced is influenced by biomass availability rate and yield. These equations ensure that the biochar storage capacity limit of each sink is not exceeded. These equations ensure that the impurity limit of each sink is not exceeded since biochar can contain potential contaminants. These equations ensure that the application rate is suitable for the soil and the corresponding crops to maximize productivity while minimizing environmental impacts. And these equations ensure that the alkalinity application rate is suitable for the soil and to prevent the soil from being excessively alkaline. And the limits set for the variables are given by these equations. Now these quantities, the biochar yield, the contaminant, nutrients, and biochar alkalinity are given here as functions of pyrolysis temperature. Pyrolysis temperature is the most critical parameter in the production of biochar as it significantly influences the yield and chemical properties of the resulting biochar. And therefore, the temperature can tailor biochar to possess certain characteristics suitable for the receiving soil. And for this reason, pyrolysis temperature is incorporated in the model to determine its effect on carbon sequestration potential and profitability of a biochar-based carbon management network, while at the same time ensuring that the quality requirements of the soil are met. Now, the succeeding slides will clearly illustrate the applicability of the model for the high-level planning of biochar-based carbon management network. So a case study is given here that represents Central Luzon region in the Philippines, which is one of the leading regions that produce agricultural crops and residual biomass resources in the country. And the semi-hypothetical case study depicts three sources, 4 sinks in a time frame of 10 years. The contaminant, nutrient, as well as the alkalinity and yield are given here as functions of pyrolysis temperature. The characteristics of the 4 sinks in which the biochar are to be applied are given in Table 3. And the assumed maximum level of contaminant in biochar that can be safely added to the soil is also given. The recommended annual application dosage is based on the range of application rates used in the literature. Now, table 5 shows the distances between the biochar sources and sinks, and the cost data for the case study are presented in Table 6. So for the results and discussion, we can see that there is a trade-off between carbon sequestration and profitability as depicted in the figure for the different values of psi. So what is psi? Psi is the risk aversion parameter, and it is incorporated in the model to account for the uncertainty arising on the difficulty of finding the level of impurity that can be tolerated by the receiving soil. The parameter psi is a measure of the extent to which the decision maker is ready to risk soil contamination. Its value can be set to 0 if no level of soil contamination can be tolerated, and 1 if the decision maker is willing to accept the soil contamination levels to reach the prescribed physical limit. Now, each point here corresponds to a particular biochar sourcing network. Let us choose a representative example, say network A. So at psi equals 1, the result of network A is shown in the table as a representative example to give a clear understanding of the model solution. The table gives the optimum amount of biochar allocated for each sink coming from each source in the network. The first and the second values in each cell show the biochar allocation during the first 2 years and last 8 years of operation, respectively. The model recommends blending of low and hybrid biochar at sink 3 during the 10-year time frame so as not to exceed the limit prescribed for each contaminant. Now, sensitivity analysis with respect to market price is also conducted, and as can be seen, the effect of biochar pricing is more significant in profit than in carbon sequestration. The figure shows the trade-off between carbon sequestration and profitability, this time for the different values of pyrolysis temperature. And it can be seen in the figure that as the temperature decreases, the system-wide net carbon sequestration and profitability increases. Again, let us choose a representative example, say network A. So this is the result of network A. Every sink has distinct soil quality characteristics and biochar can be customized in order to fit certain soil conditions. And for instance, the amount of contaminant, nutrients, as well as the level of alkalinity in biochar can vary depending on the pyrolysis temperature in which the biochar is to be produced. For example, the amount of zinc contamination received by sink 3 at 300 degrees Celsius is 215,000 grams per year during the last 8 years of operation, which is the limit prescribed for zinc at sink 3. Also, the quantity of phosphorus nutrient applied to sink 3 at 300 degrees Celsius is given, which is within the range of recommended phosphorus application rate for sink 3. The alkalinity of biochar is produced and applied to sink 3 at 300 degrees Celsius, which is within the range of recommended alkalinity application rate for sink 3. Now, in conclusion, a novel framework has been developed that provides a sustainable strategy to aid the proper deployment of biochar-based carbon management networks to contribute to climate mitigation. And it generates useful insights that can guide policymaking, such as incentivization of commercial-scale biochar-based carbon management networks. The framework is comprised of component mathematical models that capture the salient features of biochar research as currently envisioned in the literature. And looking at the bigger picture, our work can serve as the core for the development of more complex formulations in the future as the stage of knowledge evolves. And future work can focus on novel data acquisition methods for the sources and sinks. So if you're interested and you want to see further details of our research, here are our recent published journal papers. And I would like to acknowledge the Philippine Department of Science of Technology and the University of Santo Tomas for the financial support. Thank you very much for your attention.
Thank you very much, Beatriz. From Beatriz, from the audience, from the participants. I think mom, ecologist and biologist. Maybe you were shocked with the formula that you showed us.
I'm sorry, I cannot hear anything.
Other there
Very choppy po.
is no one. Hello, can you hear me, Ma'am Beatrice?
Yeah, I already hear you, sir.
Sorry, I think nobody is posting except for you. And I think this is a matter of the expertise you have
Yeah, I
with
understand.
math.
Actually, this work is an emerging application area of process systems engineering. And
Yeah,
yeah,
but we are really glad to hear about your research on this carbon management.
thank you very much.
Okay. So without any more questions, uh, I would like to thanks everyone, all of the participants, our speakers, and then the attendees for attending this session, and uh, and also for the organizer, Ma'am Giselle. And with that, I'd like to say again, thank you. Can you see me?
Di po.
May question ba? Email address.
Ah,
I don't know, murag. Ako sa connection.